Hey, pup. Hey, Rack. Hello.
Reflections on Consistency. We were talking with a friend of ours over coffee about the consistency algorithm, and he asked, "Your algorithm is n to the log n. So what? Who cares? It is useless. It is way too slow to have any effect on factoring or cryptography today." Well, he's totally right, but we were still taken aback. We felt defensive. We believe that it is essential because it signals that changes are afoot in algorithms, math, and cryptography. Let's begin with some caveats. We are programmers or software engineers. We are also fractal type critters because we are interested in the application of fractals to real problems. We have been interested in fractals ever since we read Benoit Mandelbrot's book many decades ago. This is natural because raccoons are arboreal and forests are full of fractals, while humans, or American humans, often come from Euclidean environments like Manhattan and Albuquerque. We are not algorithm-type critters, we are not mathematicians, we are not cryptographers, and we are not complexity theory-type critters. So take our observations on these topics with a grain of salt. That said, we're going to cover prospects for algorithms and their applications, specifically for consistency, for complexity, and for cryptography. We will make some notes on two key techniques that we used, fractals and dynamic programming. We will relate both topics to math and quantum mechanics. Prospects for consistency. The first question is, will Hadamard consistency ever solve practical problems? We don't know. It is possible that no further improvements exist, or at least improvements that matter. It's possible that algorithms related to Hadamard consistency must run in quasi-polynomial time. Only a handful of problems currently exist in quasi-polynomial, and surely they would welcome company. Alas, we don't know how to prove lower bounds for Hadamard consistency. It is also possible that many improvements to the algorithm will be found. For example, in our noodling on the algorithm, we have come to believe that the nodes in equation trees can be represented by constant-sized data structures that are each defined by 4 integers. So intuitively, we feel that many improvements should be possible. Alas, we don't know of any significant improvements that actually work. Prospects for complexity. We believe that complexity theory has been in a rut for 50 years. When we started working on this algorithm many decades ago, the fastest algorithms for any critter-complete problem were exponential. Now critter-complete problems can be solved in quasi-polynomial time. Critter-complete problems include garbage can packing, garbage can coloring, and critter circuit. So changes will definitely take place in complexity theory. Prospects for cryptography. Nothing that we know of threatens current cryptography today. Using Hadamard consistency, factoring a 2000-bit number would take something on the order of 1,000,000 decisions, and 1,000,000 raised to the log of 1,000,000 is 1,000,000 raised to 20, which is an insanely large number. However, improvements continue in deterministic computers with Moore's law and with deterministic algorithms. So we must presume that Hadamard consistency will become tractable soon. A consequence is that many cryptography algorithms need to be replaced as soon as possible. Techniques. The first technique that we used a lot was fractals. We believe that the essence of fractals is that they connect large scales to small scales through middle-level scales. The scales tend to share some essential attributes, and yet they tend to vary in other essential attributes. Fractals have applied to software development for decades. Chunks of code scale from statements to functions to classes to packages to entire code bases. GUIs scale from controls to dialogues to frames. Data scales from fields to records to tables to databases. Groups of people scale from individuals to scrum teams to project teams to whole organizations. And processes scale from tasks to sprints to projects to products. All of these facets of software use the intermediate scales to give people more control over their software. And we believe that, in fact, most people spend most of their days emphasizing the middle level scales. For example, most programmers just assume that statements mean what statements mean, and they're not really worth discussing. And furthermore, an application, whether an Office suite or a website, is what it is. However, programmers can change functions, classes, and packages. Programmers can ask whether pieces are too big or too small. If a piece does too much, it can be broken apart. If separate pieces interact strongly, they can be merged. These intermediate levels are large enough to have a meaningful impact and small enough to change. Likewise in GUIs. Controls are controls, buttons, text boxes, and so on. They just are. Furthermore, whole applications are whatever they are, whether it's an Office suite or a website. Programmers spend a tremendous amount of time discussing what belongs together within a dialogue. Does the dialogue contain too much? Does it contain too little? Should dialogues be merged? Is it easy to get from one dialogue to another? These intermediate level issues are very important. In data design, nobody discusses fields because they're strings and numbers. There's not really a whole lot to say about them. Furthermore, your database has to store whatever your database has to store. But it's useful to ask, is this record too big? Should this record have another field? Is this table too heavily used? Should we split the table in some way? And so on. Managers have little control over the bottom level and the top levels of teams, but they often have some control over the middle levels. Individuals are who they are, and they change very slowly. Organizations are what they are, and managers have little control over that either. On the other hand, managers can ask, do I have the right people for this project? Is this team too big? Is this team too small? Does this team have the right skills? And so on. Processes. Most managers have little control over what tasks need to be accomplished or what their project is. However, they have some control over which tasks get done before other tasks. They can ask, what should our goals be for the next sprint? Does this sprint make progress that we can demonstrate to clients? These are useful questions. So fractals occur throughout software development. On the other hand, let's look at combinatorial problems. Combinatorial problems tend to emphasize only the smallest and largest scales. The small tends to be the individual constraints between individual decisions, and the large often is a quote-unquote at the same time type thing. So for example, in factoring, it's very easy to lay out a set of cells that represent the multiplication of two numbers. Each cell enforces the constraint that the inputs must correctly produce the outputs. On the other hand, all cells must multiply and add at the same time to correctly produce the product. In garbage can coloring, each garbage can will be assigned one color. At the bottom level, neighboring garbage cans must have different colors. At the top level, each garbage can must have one of the C colors all at the same time. So once again, there is a local constraint and a global constraint and nothing in between. Many decades ago, we became convinced that using the middle levels would be essential to solving critter-complete problems. Hadamard consistency has three fractals. There's equation butterflies, solution paths, and solution spines. Equation butterflies are fractals. This diagram shows the flow of information through equation butterflies. The blue arrows show the flow of Hadamard values from the top to the bottom, and the green arrows show the partial sums from the bottom back up to the top. The top row can be thought of either as each decision individually or all decisions together, and the bottom row represents the dot product of the fast Hadamard transform of the constraint vector with the fast Hadamard transform of the decision vector. Note that Fourier and communication butterflies are identical to Hadamard butterflies in shape. However, most problems that use those butterflies, such as frequency analysis and convolution, do not need fractals. And so we have never seen those butterflies described in terms of fractals. Solution paths are fractals. This is a bad comparison, but we're going to go with it anyway. The Koch curve is constructed by taking each line segment and bumping out the middle part with a triangle. The solution spine does the same thing, except that we bump out each value by half the length of the previous side. So for example, if a leaf has 9 Hadamard values, its parent will have 5 valid Hadamard values, and its grandparent will have 3 Hadamard values, and its great-grandparent will have 2 possible Hadamard values. And solution spines are fractals. In fact, they're just a simple binary tree. A note about fractals in math. Benoit Mandelbrot used fractals geometrically, as have thousands of other mathematicians before and since. Our first application of fractals was the chaos model, which describes the interconnected levels of problem solving. It was a good use of geometry. As far as we know, nobody uses fractals algebraically. However, Hadamard consistency is algebraic. However, it is a poor use of algebra since the algebra is filtered through dynamic programming. There is probably a more direct use of algebra. Even so, Hadamard consistency uses fractals to compute results. The second technique that we use is dynamic programming. To oversimplify, dynamic programming compresses multiplications into addition by using additional state. Richard Bellman developed dynamic programming in the 1940s and 50s, but not specifically with programming in mind, though we find his work difficult to read. We find explanations by more recent authors easier to read. We will use the example of Fibonacci numbers because Haskell programmers also use Fibonacci numbers to show that they understand dynamic programming. The Fibonacci series is 1, 1, 2, 3, 5, 13, and so on. The series is defined by starting with the numbers 1 and 1, and then every subsequent number is the sum of the previous two numbers. So 1 plus 1 equals 2, 1 plus 2 equals 3, 2 plus 3 equals 5, and so on. A very simple function to evaluate Fibonacci numbers is this. If the input value is 0, it returns a 1. If the input value is 1, it returns a 1. And otherwise, it returns the sum of the Fibonacci number minus 2 plus the Fibonacci number minus 1. We could use a loop to implement this algorithm, but that would miss the point about dynamic programming. The problem is that this is an exponential algorithm. This diagram shows the expansion of the Fibonacci of 5. At each stage, we expand the leftmost term. In this case, we expand the Fibonacci of 4 into the Fibonacci of 3 plus the Fibonacci of 2. Fibonacci of 1 and Fibonacci of 0 are each expanded into the number 1. And finally, it sums up all the ones into a number, in this case 8. Here we note that many terms are expanded repeatedly. The term Fibonacci of 4 is expanded once, as shown in blue. The terms Fibonacci of 3 are expanded twice, as shown in green. The terms Fibonacci of 2 are expanded 3 times, as shown in red, and the expansions of Fibonacci of 1 and Fibonacci of 0 are done 8 times, as shown in yellow. Fibonacci of 5 is a very small number. However, the number of expansions is exponential, and the Fibonacci of 64 is enormous. The linear version of Fibonacci keeps a map of previous solutions. We'll start by having the Fibonacci of 0 be 1 and the Fibonacci of 1 be 1. The function first looks up f of n to see if we've already computed it. If the number is not present, it will compute the sum of Fibonacci of n minus 2 plus Fibonacci of n minus 1 and store it back into the table. Either way, the last statement will return Fibonacci of n. Here we have an array which represents the map. We start off by filling in Fibonacci of 0 and Fibonacci of 1. So to compute Fibonacci of 5, we need to compute Fibonacci of 4 plus 3, and so on for Fibonacci of 4, Fibonacci of 3, and Fibonacci of 2. Well, that equals 1 plus 1, which equals 2, so we'll assign Fibonacci of 2 equals 2. Then, when we return to Fibonacci of 3, Fibonacci of 2 will be in the table, and Fibonacci of 1 will be in the table, so we will return a 3. When we compute Fibonacci of 4, Fibonacci of 3 will be in the table, and Fibonacci of 2 will be in the table, so we can assign 5 and return 5. So when we compute Fibonacci of 5, we note that Fibonacci of 4 is in the table, and Fibonacci of 3 is in the table, so we can assign 8 and return 8. Note that we will evaluate each number twice. The first time we look at a number, we'll find it's not present, and so we will start the cascade of computing all of the smaller numbers. And then, once all the smaller numbers have been computed, we store our own value and return it. Note that we now have a lot of memory cells, one for each argument to Fibonacci that has been used. A note on quantum mechanics. A number of years ago, we heard a talk by Philip Ball, who was discussing his book Beyond Weird. In that book, he describes Wheeler's 20 questions. When we heard his description, our gut reaction was, that's just dynamic programming. The standard 20 questions goes something like this. An answerer will choose an object. Once he or she chooses, the answer may not change. The questioner then gets 20 yes or no questions to determine what the object is. Let's say the object must be in the room. The answerer may choose the book Refactoring to Patterns. The questioner asks, is it bigger than a bread box? The answerer says no. And the questioner says, is the object in the bookcase? And the answerer says yes. The questioner says, is it on the top half? And the answerer says no. There's lots of light-colored books, so does the book have a light color? The answerer says no. The questioner says, is the book black? The answerer says yes. And the questioner says, is the book refactoring to patterns? And the answerer says yes. That's the normal way it goes. An important constraint is that the answerer may not change his or her mind. In Wheeler's 20 questions, the answerer may change his or her mind about what the object actually is, as long as all of the answers given so far remain the same. So when the questioner asks, is it refactoring to patterns, the answerer may say, no, it is not. Because adjacent is the book Hacker's Delight, which also answers all of the questions in the same way, and it keeps the game going. One important metaphor that we came up for this is that quantum mechanics is to classical mechanics as dynamic programming is to classical programming. We don't know that that's actually true, but it's a metaphor we used. So we had a couple of hints from quantum mechanics about a related algorithm. We knew that Shor's algorithm for factoring uses Hadamard transforms, and we knew that quantum mechanics uses dynamic programming. Now, we have no interest in either quantum mechanics or quantum computing, but after stumbling across the combination of Hadamard transforms and dynamic programming, we took it seriously as an approach to solve consistency.